My name is Matthew Garibaldi. Richard is really leading this section. He's our clinical chief at the Orthopedic Institute. Sounds like some of you may know him, Richard Dean, and he comes to UCSF with a great deal of private practice experience in the private sector, and quite frankly, he's probably one of the most creative clinicians I've ever come across. So he'll have a lot to offer tonight. Excuse me, and he's also chairs or runs our technology and innovation committee for OMP, so he's the appropriate person to be speaking, and I'll jump in here and there and give a couple thoughts on knees and upper extremity as well. So without further ado, I'll hand this over to Richard Dean.
Thank you, Matthew. All right, good evening, guys. Thanks for coming. Like Matthew said, I am sort of the clinical chief when it comes to prosthetics at UCSF, and I really feel that prosthetics is one of these realms that really brings back a lot of life back to the users. You know, after losing a limb, it's really like losing a loved one, and to be able to restore that aspect of someone's life, get them back to walking, getting them back to doing physical activity and sports is kind of magical. So I started my presentation with a quote from Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic. Getting someone back to walking, back to life, truly is magical. If you don't understand that technology, it really does look like magic. So in talking about prosthetic technology, I want to make it kind of clear what type of prostheses or what kind of prosthetic stuff we're talking about. By definition, a prosthetic device is an artificial device to replace or augment a missing or impaired part of the body. So these prostheses can be internal or external. Internal ones would be like a total knee replacement, things that are embedded into the bone. On your left, you'll see a sample of total knee, and on the right, a total hip. Or it could also be something like a dental implant, things all embedded into the body, internal to the body. However, today we're going to be talking about external prostheses. The external prostheses can then also be classified as restorative or functional. Some restoration style prostheses might be an ear replacement or even a nose replacement. These are made of silicone, painted to be very lifelike, and they serve a function in restoring symmetry, improving cosmesis, also improving self-esteem for the user as well. However, they don't restore function. Getting a prosthetic ear doesn't allow you to hear again from that side, or getting a prosthetic nose doesn't allow you to, get this the sense of smell back. So we're going to be talking about external functional prostheses, and for the most part, that's going to look like a prosthetic leg or a prosthetic arm. As we look at prosthetic devices, it is pertinent to include orthotic devices. The two fields are very intertwined, and so I just want to make that clarification. I think for our PT students, you guys are pretty clear the difference between the two. However, a lot of people don't know the difference when it comes to a orthosis. It's going to be an orthopedic device meant to support an existing limb, whereas of course the prosthesis is going to be there to replace a missing limb. We do get some patients that come in as orthotic users and describe their device as being their prosthesis or their prosthetic device. So I just want to make that clear. Okay, so as we talk about the technology, we want to first sort of break down a prosthesis. What makes up a prosthesis? What's the anatomy? The first section is going to be the socket. This is essentially our human interface. This will be how the devices connect to the user, how they can control the device. And it's important for these sections to be very well-fitting, very intimate to the body. It improves comfort, improves control, and improves patient satisfaction. This is sort of analogous to maybe, a glove for a hand or a shoe for a foot. If the shoe's 3 sizes too big, it makes it very difficult to walk or even to run. Conversely, if it's too tight, you got great control, but it's not comfortable to wear for more than an hour or so. The next section of the prosthesis may have a joint replacement. This could be an elbow, like on the left, or maybe a knee joint on the right, and those will allow to mimic the human body, return back range of motion, being able to bend at the knee to sit down, or bend at the elbow to pick up an item, bring your hand to your face to feed yourself. And then the last part will be a terminal device. This could be a hand that does the grasping for objects, or it could be a foot that interfaces to the ground, provides that stable platform for standing, and progression when walking forward. You may end up having additional joints in the hand. It could be a wrist unit, allowing for rotation with pronation or supination. There also might be a wrist flexion unit to allow for flexion and extension of the wrist. Conversely, with the leg, you might have a torsion unit between the foot and the knee, allowing for twisting between the two sections, or even an ankle joint that allows for plantar flexion, which is toes down, or dorsiflexion, toes up. No offense to the PT students. I know you guys know that part already. Okay, so let's talk about prosthetic sockets, since it is kind of one of the most important aspects of a prosthesis. A little historical perspective, old sockets were made out of wood. Back during the Civil War era, James Hanger made his socket by using barrel staves, whittled wood, and use that as the interface to attach the prosthesis to the residual limb. There also were, like the ones you see here, made from solid blocks of wood, where a practitioner or technician would actually carve out the blocks of wood, creating a hollow space to insert the residual limb. This was a long, painstaking process, not very accurate. They would use measurements of the limb, carve out some of the wood, patient try it on if it was comfortable, great. If not, carve out more wood. There wasn't a lot of scientific thought used to make these devices. Luckily, nowadays we can do things a little bit better, and so we actually take a mold of patient's residual limb. One of the conventional ways is to use plaster, and that plaster is essentially just hand wrapped around the residual limb and molded in. The plaster can be massaged, it can be compressed. This allows kind of really good direct patient feedback. While the practitioner is casting, we can squeeze a limb, put pressure in an area that we want to load the limb. Patient can respond back, yes, that's comfortable, or no, that's too tight, that's uncomfortable, that's painful. And so once the plaster's set, it essentially yields a negative mold of the patient's limb. That negative mold can then be filled with liquid plaster. The negative mold will be stripped off, and then we're left with a positive mold, or essentially a statue of their limb. That mold, as you see in the bottom left, can be carved and shaped based upon what forces we want to apply to the limb during standing. The mold can also be modified by adding more plaster and relieving certain areas. In certain areas you might want to relieve bony prominences like fibular head, distal end of a tibia that has been cut, or maybe an area that has an aroma or a nerve bundle that's really sensitive to the patient. Once all that's completed, the next stage would move into fabrication. That plaster model is then put into a fabrication jig where hot plastic is essentially draped over the model and vacuum is applied. That vacuum sucks the air out, molding the plastic directly to the model, reflecting all those shapes and contours that the practitioner has built into there. Makes for an exact fit. The plaster once the plastic is cooled, the plaster is removed, and you're left with what we call a test socket, which is essentially back to a negative model. Clear plastic so we can make visual assessments. Once a patient puts their limb into the socket, we can see areas that are gapping, areas that are of high pressure. You might see some blanching of the skin. You might see a lot of compression of the tissue. And being plastic, we're able to heat mold it and reshape that. We can make it tighter, make it looser to increase the patient's comfort. The plastic test socket is also durable enough for us to test with the patient standing and walking. And this really gives us the ability to confirm that we've done a good job fitting the device, make additional adjustments, and the patient can try this out for an hour, a day. It's possible to even send the patient home for a week on a test socket and really get long-term use on it and let us know if it's ready to be finalized. This process can be repeated multiple times. You could re-pour the plaster, make more modifications, make a new check socket. At some point, you should be done with it and hopefully yielding a comfortable device. And then moving to final fabrication, the plaster model is then laid up with carbon fiber and other fabric materials. Those materials are embedded with acrylic and epoxy resins that will then cure underneath vacuum. So again, bringing that shape to match the plaster model. And your final device won't be clear, but it will be rigid, durable, and lightweight. We took this from the aerospace industry with all their cool materials and everything. Okay, so let's talk about the digital world. That process was very manual, requires hand skills and years of learning. Nowadays we have computers, and so someone smart decided to use the 3D world and do some digital scanning. Here we have a patient's residual limb and a laser or light scanner being used to get a digital capture of the limb. The beautiful thing about this is the laser scanner has accuracy of about 0.5 millimeter. So it can really capture all the shapes, all the contours, give precise measurements. Can be done in about 5 minutes. And one of the great things is the reproducibility. You don't have to have 20 years in the field to take a great cast or great mold of the patient. You can fire up the computer and with about 15 minutes of instruction, be able to take a scan just as good as somebody who's got 20 years into the field. One of the downsides, however, is because you're not applying any compression or squeezing the limb, you don't get that direct patient feedback. Once it's been scanned in, a digital CAD file is created. There's software out there that will then allow you to do essentially what we do in plaster. You can reduce areas, you can build up areas based upon how you want that socket to fit. If you want it to be tighter or to be looser, or if you want a global change, you can put in parameters to shrink the socket by 2%, 3%, or 15.85% accurately. Whereas if you do it by hand plaster, it would be very difficult to do. Once you have a digital model, there are 2 routes that you can use for fabrication. The first one would be a foam carving, where that digital file is put to a machine that has a robotic arm with a cutting tip to the end of it. That cutting device will basically take a block of foam, cut all the way around it to yield essentially what would be similar to the plaster model, except instead of being made of plaster, it's made of foam. And you didn't spend half an hour making it, the carver cut it out in about 2 minutes. This foam model can then be taken back to the vacuum forming station, and you can make it test socket the same way you did with the plaster. Nice things about the foam, you can also make additional changes by carving using the same hand tools as you did with plaster, or you can add plaster and create more release in the device. The other method of fabricating from a digital file would be 3D printing. Of course, this has been really popular in the media lately, where the printers will basically use additive manufacturing and print out the socket, not using a foam block or plaster, not having a positive model or any waste in that sense. They are durable enough to be used for test socket fittings. At this point, they're not quite durable enough to be used for definitive. They haven't quite matched the strength and durability of the carbon fiber to this point. Okay, so now that we know how sockets are made, let's talk about how we end up designing the socket. We're going to start with the transtibial sockets. Transtibial, just to be clear, would be a below the knee style socket. So trans being transected through the tibia, which all of our PT students know, is going to be essentially our shin bone. So it's going to be a below the knee socket. The most conventional style of below the knee socket is going to be we'll call it a PTB, or a patellar tendon bearing socket. This socket design has very specific loading areas. One being the patellar tendon, that's the big tendon just below your kneecap. The counterforce in the popliteal, keeping it tight and keeping a tight AP to essentially push the limb forward onto that patellar tendon to bear the weight. And then your medial tibial flare as well too. So that's going to be the inside aspect of your tibia as it curves upwards. All those areas are sort of areas of high tolerance for pressure. Conversely, you also have areas of high sensitivity, fibular head again, distal end of the tibia, all areas that patients can't tolerate taking weight. When looking at a PTB socket, you'll notice a lot of very specific contours. Here in the socket, you'll notice there's kind of a deep groove, patellar groove for that tendon, designed to sort of dig into the tendon, which is not innervated, so it's fairly tolerant of pressure. Take a lot of weight here, and then a tight posterior wall. And as the compress the tissue to maintain contact to that patellar groove, then there's usually a large reverse flare curvature here to cradle the tissue that is then essentially sort of pooching out the top of the socket. So progressing on from a patellar tendon bearing socket was the total surface bearing socket. And this type of socket really came about because of materials that came out silicone, other types of gel, TPE, that patients would essentially roll on a gel liner to their limb. This provided some cushioning as well as uniformed their limb for global changes. So as the name suggests, the weight bearing is now taken across the entire limb, not just in key specific areas. This is great because then those 2 or 3 key areas don't have a high pressure from weight bearing. Now all that weight is then distributed evenly across the limb, thereby decreasing the pressure at any specific point. And you'll notice in the socket here, it's a lot more uniform. There aren't these big contours or curvatures digging into the limb or reversing out away from the limb. Because again, we're not loading 2 or 3 specific spots. We're really trying to load the entire limb. This style of socket really relies on hydrostatic pressure and compression of the whole limb to hold up the patient and make them comfortable and to provide the control. So from the total surface bearing socket came elevated vacuum sockets. The diagram here illustrates the method of how fluid would flow out of the limb as the patient's walking, doing activity throughout the day. Fluid actually move out of the limb, reducing the volume of the limb and having the patient's limb drop down to the bottom of the socket, then increasing the pressure at the very bottom, generally very painfully. By applying vacuum between the surface of the liner and the inner wall of the socket, we create essentially a fluid balance. Fluid is escaping, but then also being pulled back in via the vacuum. This allows for a more uniform and consistent volume of the limb, and the pressure around the limb stays consistent even throughout the day. The vacuum pumps can come in a couple different forms. On the left here, we have a mechanical pump. This pump is operated essentially by the patient's weight. Every step they take, that piston's compressing, it's pulling air out of the socket and evacuating. Similar to a bike pump, but instead of air going in, air is coming out. On the right, we have an electronic pump. This pump is battery operated, and the user will turn the pump on when they don their leg, and this will evacuate the air to a specified PSI. That's usually based and set via the practitioner. Once it hits that specific level of pressure, the pump turns off. User can walk around, do whatever they want to. If they end up having a leak or they sit down for a while and air enters into the socket, decreasing their hold and their the contact, the pump will automatically turn back on, hit that level of vacuum, and then shut back off. So the user doesn't really need to do much in way of paying attention to their negative pressure. When this system came about, it was very useful for diabetic populations, people who had a lot of ulcers that would develop on their limb. The elevated vacuum system really did a good job in promoting healing of ulcers because it had that fluid balance and kept a lot of fluids moving in and out of the limb. All right, and then we progress into adjustable sockets. Up till now, everything's been a solid socket. It has been static and rigid. Once it's done and made final, not a whole lot of adjusting can occur. So recently, there's been adjustable sockets that have come about. The adjustability can come via specific panels. The one we see here has 3 panels, one in the popliteal region, the medial tibial flare, and probably a pretibial region. And these are generally areas that are able to take high pressure. So the user can adjust their fit throughout the day. If they feel a little bit loose, they can crank it up, get a little more compression, feel more comfortable. If they can do something like play basketball, some kind of high activity, they can get more control out of that. Or if they end up sitting down, watching a movie, being in a lecture, feels too tight, they can pop it loose, let the tissue and all the fluid relax. The adjustability can also come more globally, either by the socket in the middle, where it tends to have more of a front to back or an AP closure to account for the adjustability aspect, or the socket on the left where it's more circumferential. As the user tightens it, it closes in the circumference of the socket, increasing the pressure and the control. Okay, so we're going to move into the transfemoral sockets and see how they've progressed over time. The most conventional is the quad socket. Sorry, we talk about transfemoral. Now we're talking cutting at the femur, which essentially would be an above the knee amputee. The quad socket is aptly named because it looks like a square. It's got 4 sides. Looking at the picture down, bottom right, this would be a cross view looking down into the socket with the dark area being the femur and the surrounding muscles and tissues, and then the wall of the socket all the way around. This diagram gives you a good representation of anterior, or the front of the socket, posterior, the back of the socket, lateral, which would be the outside or away from the midline of the body, and then the medial side, which is towards the midline or the inner side of the thigh. And so with that orientation, we can tell that this is a socket for a right transfemoral user. The design of the socket is to bring the weight-bearing pressure up to the ischium. And looking at this diagram here, we notice the transected femur doesn't have any areas to take loading stress. Once the femur is cut, there's no weight-bearing surfaces. So bearing weight at the very distal end of a cut femur is very uncomfortable and very painful. So we have to move more proximal up to the pelvis. So we'll see here the ischial tuberosity is now resting on a shelf for vertical load and weight bearing. On the left is a picture of a quad socket, and the person is pointing at where the ischium actually sits in the socket. In order to maintain that ischial placement in the socket, it does require to have a tight AP, or anterior dimension. Otherwise, the ischium will sort of fall inside the socket and cause the bottom of the femur to hit the bottom of the socket and be very uncomfortable. For those of you that don't know, the ischium here is essentially our butt bone, that part that gets really uncomfortable when you sit in a hard chair or ride a bike for a long time. So not an intuitive spot to take pressure, but again, without any weight-bearing surfaces on a cut femur, that's the next available space for vertical load. One of the problems with this socket design is there isn't any stability inherent in the socket design. That ischium that takes a lot of the weight bearing can essentially slide back and forth on that shelf. Many of you students might know that as Trendelenburg gait. So then the next development of the transfemoral sockets is the ischial containment socket. Again, here on the left, we have the same picture of the quad socket with the ischium essentially sitting on top of the shelf and able to move left to right. This diagram up here is the ischial containment socket, where the ischium actually sits inside the socket. So essentially there's a vertical wall from that shelf to contain the ischium. And then the lateral wall goes up over the troch and really locks in the femur and the pelvis in what we call a skeletal ML dimension. And that really provides a lot of pelvic stability during single limb support. Here's a picture of kind of a finished socket. And you can notice the high medial wall. So the ischium will sit on the shelf here, and then the medial wall will contain it. So if you can imagine your butt bone sitting on that hard bike seat, now imagine a wall on the inside of that containing it to keep it from sliding around. It can be a very invasive socket. And up till now, just like the transtibial socket designs, we've been looking at solid sockets. Solid walls, again, rely on hydrostatic pressure. A little diagram here. So the blue line would represent the socket. The inner gray circle is the bone, and the empty space in between would be fluid, soft tissue, muscle, and the compression essentially would provide force into the limb, and the limb and the hydrostatic pressure would push outwards to the socket. The downside of this design is if the patient's limb reduces in volume, essentially the socket becomes very loose. So one of the developments in transfemoral sockets is the vector design socket. Matthew's actually been a big part of this and developing it at UCSF. The vector stands for Vector Enhanced Compression and Tissue Relief. In the diagram here, the blue line again is our socket. So you'll notice it's driven much closer to the femur, and in order to do so, the muscle, soft tissue, and fluid need to escape somewhere else. So the socket itself is actually open, and these tissue reliefs here would coincide with kind of the white or the beige areas in the picture here. So you have tissue coming out in order to let the socket drive in nice and tight and stabilize the femur. By stabilizing the femur in this way, we don't rely on the containment of the ischium. So the shelf can be just at the ischial level and really keep all the trim lines much lower and much more comfortable for the user. So the future of the sockets, though, instead of having to deal with hard sockets, high trim lines, invasive trim lines, someone thought about, hey, let's eliminate the socket. And how do we do that? If we don't have a socket, The next thing is to then go and implant into the bone. So this is being done here at UCSF. The illustration here shows the bone, and there is a fixture screw that gets surgically implanted into the femur. That fixture screw, if put under a microscope, actually shows a lot of porous openings, so the bone can actually grow into the fixture screw and really truly integrate it to the human body. The next piece would be an abutment that interfaces to the fixture screw and is transdermal, so it actually crosses the skin, and the other end of the abutment screw would interface to the prosthesis. This allows the user to then take their weight bearing instead of on their ischium, actually through their skeleton back to how our bodies are normally and naturally designed to do so. One of the unique things about the system that we use here is the axor component. This piece would thread onto the abutment, and this is something that the user can do. This would be the section where the user would take on and off at nighttime when they go to bed or get up in the morning to put it on. It's just a hand tool. It works just like a hand drill and a chuck. You loosen it and the jaws open and close. And so the user will be able to put it on themselves, take it off every night. And the really unique thing about the axor is that it essentially works as a torsion brake release mechanism. If the patient does some kind of high activity, that puts a lot of stress on the prosthesis and their limb, maybe potentially falls, instead of all that torque and that force going into their limb, potentially breaking their femur or loosening the fixture screw, the axor actually releases itself, taking all the stress and dissipating it away. So here we have a video of patient donning the axor.
Can you move it around like this? Cool. And then switch down. Cool.
So you'll notice no socket coming up the thigh, no compression, no skin discomfort. Weight bearing goes directly through the femur and back to his pelvis, just the way he used to stand before his amputation. Okay, so now we're going to go into prosthetic knees.
Okay, now that you know everything you need to know about sockets, we're going to talk about prosthetic knees. So of course, a prosthetic knee joint is required only for any amputation above the knee, right? So that's going to be a knee disarticulation amputation, transfemoral through the femur, anything transecting the femur, a hip disarticulation amputation, hemipelvectomy, and so on and so forth. So just to understand a little bit of a historical perspective of knees, this is kind of a fun little bit of history. So dating as far back as the 1500s, we know of Ambrose Paré, who was the official barber and surgeon of the kings of France in the 1600s. Interesting combination of titles. And he introduced modern amputation techniques and procedures for the medical community, and in fact designed prostheses, which was rare then, and it's unheard of now that the amputating surgeon would also provide the prosthesis, so that was kind of unique. But what he's really known for is the creation of these custom prostheses that had a locking mechanism or a locking knee in the stance phase of gait to provide stability for the patient. Interestingly enough, we employ some of these same designs still yet today. So prosthetic knees are really stratified into really four main categories: mechanical knees, pneumatic knees, hydraulic knees, and microprocessor knees. We won't talk about pneumatic knees because we don't use them as commonly anymore. And then I'll also talk about a little bit more of an advanced technology known as powered knees, and we'll go into that in a bit. So there have been several mechanical knees that have come to market over the past century, all of varying unique designs. These are typically devices that are used for lower level amputees who are walking at a fixed cadence. They're relatively light and inexpensive, but they all have three basic features. stance phase stability. So if you weight bear on the knee, it has some sort of a braking mechanism to prevent the knee from falling, or braking and the patient from falling in the stance phase of gait. They all have, or most of them have, a friction adjustment that acts as a decelerator of the knee through the swing phase of gait. Another way to say that is the friction adjustment acts as your quadricep and your hamstring complex through swing, preventing excessive knee flexion and extension through swing. And many of them have what is referred to as an extension assist to help advance the limb from the end of stance and through the swing phase of gait. The problem with the mechanical knee, again, they're really designed for lower level amputees, especially nowadays, is that the friction adjustment used to decelerate the knee through swing to prevent excessive heel rise or knee flexion or excessive terminal impact or an abrupt extension is really insufficient. This friction adjustment is insufficient. And so the advent of, or the incorporation of hydraulic fluid into the knee unit was seen some time ago, and these are early examples of early hydraulic knee units that helped dampen the swing or the pendulum type of action of the lower extremity through swing. The way it functions is actually quite simple, and a common usage you see is a hydraulic cylinder on a door. So if you push lightly on that door, few valves will open, not a lot of hydraulic fluid will rush into the cylinder heads, and it'll be easy to open that door. If you push hard, conversely, more valves will open, more fluid will rush into the cylinder head, and it'll be very hard to open. So that prevents the door from swinging and bumping into somebody or something along those lines. It works very similarly in a hydraulic knee unit. You walk fast and quickly, aggressively, more valves open, more fluid rushes in, and it's stiff to prevent this excessive knee motion. Conversely, if you walk slow, it's easier to bend, but it won't. It will be easier for the user to bend. Excuse me, without a lot of excessive hydraulic resistance. So the problem with those early knee units was that although they addressed the swing phase issues that amputees were experiencing, they didn't address the stance phase issues. And what I mean by that is there was no stance resistance, so patients were falling. So the advent of the Malk knee unit really addressed much of that, in that it allowed for stance phase hydraulic resistance as well. So in theory, this knee did it all. It was a great knee. It was used for many years, still used in many cases. The problem is we experienced many environmental barriers throughout the day. We could stumble by catching our toe on a root or an uneven sidewalk. There are a variety of environmental circumstances in which a standard mechanical knee isn't always the best option. You need something that essentially has a brain and can think for the amputee to prevent them from falling. So in the early to mid-90s, there were a number of microprocessor knee units, or MPKs as we call them, that were introduced to the marketplace. The most notable knee pictured in the upper right is the C-Leg, a product designed by a German prosthetic manufacturer by the name of Ottobock. And it came to be the most reliable and is considered was considered the best functioning microprocessor knee unit of the time, and I think in many ways it still is today. And so the concept is this: there's a central processing unit at the top of the knee that reads where the patient is in gait. How does that happen? So the pylon, which is pictured to the right of the knee, actually has strain gauges built into it. So that strain gauges reads toe and heel loads as ground reaction forces. That data is then transmitted to the CPU at the top of the knee, and it is monitoring the patient's gait at 50 times per second. with that information, it's able to assess that the patient the knee is giving the appropriate amount of hydraulic resistance necessary for the phase of gait the patient is in, and thus can assess whether or not the patient is stumbling, whether or not they want to descend a ramp or stairs, and will give them the exact appropriate amount of hydraulic resistance for the phase of gait they're in or the situation that they may find themselves in. So the next most logical step of prosthetic innovation beyond the sea leg, which is essentially a knee that allows for eccentric contraction or lengthening of the quadricep complex. Descending a ramp or descending a stair is a concentric lengthening contraction of that muscle. How do you go upstairs? How do you go up a ramp? You need a concentric contraction or a powered knee. So that's the next innovation where many biomechanical engineers have focused a lot of their energy. So this is a powered knee that allows for both concentric and eccentric contraction, and it simulates the true function of a quadricep muscle group. The problem is that many researchers didn't realize the power requirement for such a unit and the power, the battery pack size and weight that was required to make something like this happen. And so these units ended up being very large and very heavy, and still today are seen as being somewhat investigational by clinicians, researchers, and payers alike. So this concept of a synergistic relationship between foot and knee, between the ankle, which is where all the power is derived in a normal human lower extremity, and the knee, it really remains the sort of ultimate or preeminent goal of creating the very best transfemoral prosthesis. So this combination of net power derived from both ankle and knee is very interesting to researchers, and there's a lot of work surrounding this area in many institutions across the country. So it's a joint project right now between Vanderbilt's Center for Intelligent Mechatronics and the Rehab Institute at Chicago's Bionic Medicine, Center for Bionic Medicine, where they've created this bionic knee. This was featured on I think a CNN or a 60-minute segment where this gentleman walked up 103 flights of a Chicago skyscraper just to demonstrate how amazing this knee ankle net power generation can be. Something that many of us with two sound limbs couldn't even do. So it's a pretty impressive feat. And now we'll move to prosthetic feet.
Awesome. So all that great work that knee does needs to integrate somewhere to the ground so that it's going to go to the foot. And one of the first feet that was made out there was by Dr. Douglas Bly, which he made it from a polished ivory ball and a lot of rubber tendons that allowed a lot of ankle inversion, eversion, plantar and dorsiflexion, which we don't use anymore today. But instead, one of the conventional feet we do use happens to be made of wood and foam. So this is called a satch foot. It stands for solid ankle cushioned heel. So there isn't any plantar flexion or dorsiflexion in the foot, but instead the cushioned heel down the bottom would serve as a pseudo plantar flexion moment during initial contact and loading response. The wooden keel provides the stiffness and stability for mid-stance. And then you'll notice that the wood keel ends just by the met heads, and the foam continues to allow for essentially dorsiflexion of the toes or rolling forward into terminal stance. Very basic, but still very stable. And we use it a lot still nowadays for our brand new amputees who don't have the ability to balance themselves over maybe a dynamic foot or a foot that has power. So it's a great starting point. From there, as materials improved and became readily available, we moved into energy storage and return feet. So in the bottom picture, still a similar design to the satch foot. We'll still have some foam or maybe a polyurethane bumper in the heel to provide shock absorption and that pseudo plantar flexion. but now the keel of the foot is made of Delrin, various plastics, even maybe carbon fiber. So as the patient progresses forward, rolls over the keel, essentially like a diving board, it stores that energy as it deflects, and then when they come to that terminal stance and pre-swing, that energy is sort of rebounded back, and some of the energy is given back to the user, decreasing their need to use energy as they're walking. We've also developed some articulated feet, so bringing in an actual ankle joint, usually across a single axis, pivoting. This allows for true plantar flexion and true dorsiflexion of the foot, so going up and down hills made it a lot easier for amputees. But the articulation can't just be a free swinging hinge. Just like the mechanical knees, it needs to have some sort of braking force or some sort of resistance so the patient can actually balance on that. Earlier versions would use urethane bumpers or rubber bumpers in the posterior and the front to slow it down. This particular foot here uses hydraulic cylinders, so we can adjust how quickly that plantar flexion occurs or how quickly the dorsiflexion occurs as the patient moves into terminal stance. Then we get into some more exciting feet, which I think a lot of people are kind of familiar with. That's the dynamic response feet, made fully of carbon fiber. These feet take a page from the energy storage and return foot and take it farther. Now we see over in the keel is continuous from the forefoot all the way up the shank of the foot. At some point the socket would be attached up here, so now you have a much longer lever arm to deflect, to store energy, and then return back to the user. Everyone I think nowadays is pretty familiar with the prosthetic running feet, especially after Oscar ran in the Olympics, which essentially, you'll notice the design is slightly different, a larger curvature for more energy storage and return, but also no heel. Mechanics of running don't really have you heel striking, but in the prosthetic walking feet, there still is a heel put in there so patients can balance, still have a heel-toe gait, but still getting all the energy and return back. And these are the most common feet for active users out there. Anybody who walks kind of unassisted out in the community, so they're pretty common, even though you don't see them, walking with a blade. A lot of them can walk very well and even jog in some of these non-running dynamic response feet. And so the feet have really started to progress into follow the knees and now have microprocessor controls. So that articulated foot we saw earlier with the hydraulic cylinder in it now gets a computer to control it, as opposed to just a passive cylinder. The computer, similar to the knee, is reading strain gauges. Some of them have accelerometers in them, so they'll kind of know where the foot is in space. They'll have, they'll be able to read sort of the patient's speed and then adjust that hydraulic cylinder or some kind of torsion unit to change the rate of movement in plantar flexion or in dorsiflexion. Some have small motors in them, which will dorsiflex the foot, help with going uphill, or dorsiflexing so you can clear stairs when climbing up and down the stairs. However, they're still on the passive side of things. There isn't any active plantar flexion or propulsion when walking. But that would then go into the next realm of bionic feet. These are now out in the market. They are not highly used, mostly because from a payer standpoint, but our friend Dr. Hugh over at MIT has designed the Biome. I think it's maybe got a new name now, but it's the first prosthetic foot that actually has powered propulsion, powered plantar flexion in it. There are videos of bilateral below-knee amputees running uphill with these feet, which is not something that would require a lot more energy to do in the past. One of the downsides of the foot, similar to the powered knee, is the amount of energy it takes in order to power the torque and the motor. So you'll notice the battery here is very similar to like a drill battery. Require that much power, and it only lasts about 4 to 5 hours of the day. So you usually have to change out 2 or 3 batteries to get through the day. Weight of the bionic foot, almost like 10 pounds, which ends up being quite a bit at the end of a prosthesis. But as technology gets better, it's already getting smaller, getting lighter, and hopefully, all the insurance companies will start paying for them more so we can fit more of them on patients. All right, we'll move to upper extremity prosthetics.
Okay, so on to the world of upper extremity prosthetics. So another fun historical slide. This gentleman in the upper right hand was a German imperial knight and a mercenary, actually, who lost his one of his arms, hand in fact, in a battle. And what he designed for himself was one of the first recorded multi-articulating functional upper extremity prostheses. And interestingly enough, we did not see multi-articulating prosthetic hands in the marketplace until maybe about 7 or 8 years ago. So it took a while for things to come full circle. Another interesting historical slide. So following World War II, the Surgeon General at the time realized that the current state of prosthetic innovation at the time, especially in the upper extremity arena, was lacking, and they launched an initiative to improve care and functional outcomes for these patients. So the U.S. brokered a deal with several small private developers to compete, essentially, to create the next latest and greatest upper extremity prosthesis. And sort of the net result of all of that is what we now know as external powered prosthetics, or more commonly known as myoelectric prosthetics. And so in the bottom right is an example of the schematic of one of the first iterations of that. And we use very much, you'll see in a couple of slides here in a second, we use very much the same setup with two surface electrodes placed in antagonistic positions with a battery. The hand they use uses pneumatic actuators. We don't use that anymore. But it's just amazing that in many ways we haven't advanced as quickly as we would like to. So upper extremity, again, just to stratify the different categories, it's broken out between passive functional or cosmetic prosthetics, body-powered or conventional prosthetics, also known as cable-driven devices, and then external powered devices. The external power is the battery, essentially, and a motor is what drives it. But they can be powered either through myoelectrics, meaning a sensor placed, a surface electrode on the skin, or maybe a switch or a transducer. Those are the three main types, and we'll talk about other types of prosthetics moving forward. So passive functional devices are just that in the name. They're passive in nature. The hands don't articulate in any real way other than perhaps passively positioning them with a contralateral hand. Typically, most of these hands are static in their position. Most patients seek out these devices because they are quite cosmetic and appealing to the eye, but they have a function as well. These hands can be used to perhaps stabilize a piece of paper when writing. It could be used to stabilize a large object for bimanual dexterity when picking up an object. So they can be quite functional as well. I also find that just adding the prosthesis creates symmetry in the spine of the paraspinal muscles and of the trunk musculature as well. So there's a lot of reasons why someone would use a cosmetic prosthesis. So we don't call them cosmetic prostheses for that reason. We call them passive functional. So body-powered devices are really the mainstay of prosthetics. You know, a lot of times when people think of an upper extremity prosthesis, they think of the hook, a cable-driven device, and rightfully so. They've been used for a number of years, and they're still very, very functional, and we use them today. So the concept is simple. You're extrapolating gross body motion to elicit a function of your terminal device or your hand. The terminal device can be a hook or a hand. The terminal device is a broad term that we use. So in this case, we use shoulder protraction, glenohumeral flexion to provide excursion on a cable which is attached to a harness that a patient wears, and that cable is pulled, and thus that elicits the terminal device activation, or the opening of the hook. As you relax after protracting, you retract, the terminal device will then close. The amount of pinch force is really dependent upon the number of bands or springs incorporated in that terminal device. So though we are no longer using pneumatically driven hands, like I was saying earlier, some of the same basic principles of external powered myoelectric devices still exist today. Basically, how it works is the central nervous system elicits an action potential which travels down a motor neuron, which then creates flexion or contraction of a muscle in the residual segment. Of course, that contraction has electrical activity about it, which the surface electrode placed on the skin picks up, rectifies, and actually converts to a voltage, which is then sent to a circuit in the hand, or the central the CPU in the hand, to elicit a particular function based upon however we decide to program it. So, believe it or not, this is it sounds complicated, but it is a continuous process from thought to function. So myoelectrics, again, use EMG signals to control these devices, myoelectric devices, electromyographic signals. And this is a basic setup of most myoelectric devices. So either you have whichever hand or terminal device you want to use, be it a hand or be it a work hook. Moving right is actually a motorized wrist. So for example, if you have a higher level transradial level amputation, you no longer have as much supination and pronation as you normally would have had. So you can use a motorized unit to simulate that. The two devices stemming off of the motor are actually electrodes, or the two little leads. Those are placed on antagonistic muscle groups opposite contractions. So again, in the instance or the example of a transradial level amputation, you have forearm flexors and forearm extensors. The forearm flexors typically would be used to close the hand, and the forearm extensors would be used to open the hand. And then in the middle there's a battery that's pictured. Those are the basic components of a myoelectric system. So greater exploration in hand function has led to the development of multi-articulating individually powered digits. This concept obviously wasn't revolutionary, as we had discussed earlier. It was obvious that we needed more dexterity than the basic dynamic tripod of most of the early hands. The problem is the hands were doing really amazing things and had all this great individual digit manipulation, but we couldn't control it, and in many ways we still can't today. Which brings us to Dr. Kaiken, who developed targeted muscle reinnervation. So in our higher level amputees, perhaps in a shoulder disarticulation amputation or an interscapular thoracic level amputation where the entire shoulder girdle is missing, trying to utilize those really fancy hands can be quite difficult with crude motions, gross body motions with a cable, or even just using a pectoralis muscle, which is not very intuitive, to fire your pec, to elicit an EMG signal, to bend your elbow, and to bend your hand. Patients want to think about bending their elbow, and then the elbow bends. Well, how do you do that? So TMR is very complex and yet very simple, so I'll explain it. So in the case of a shoulder disarticulation or interscapular thoracic amputation, the nerves that serve biceps, which is no longer there, right? And this would be the sort of the host muscle or the targeted muscle, is no longer there. The entire extremity is gone. But the muscle that serves it, in this case musculocutaneous, which would serve biceps to flex the elbow, is there. it's safely nested in your brachial plexus. So you can reroute or redirect or reinnervate that, reroute that nerve and reinnervate it to an existing muscle group. So you could redirect it to pectoralis major, for example. And when you think about bending your elbow, now your pectoralis fires, we can pull off EMG signals from that and reroute that to a motorized elbow. So now you're thinking about bending your elbow, and you really are. It's pretty cool stuff. So it's interesting how history tends to repeat itself, similar to the apparent deficit after World War II. At the time, the state of upper extremity technology, following our most recent military campaign in the Middle East, there had been a similar sentiment. And so as a result, there have been millions of DARPA dollars invested into oftentimes private sector projects. The grant criteria for these DARPA grants has very specific inclusionary criteria, the most notable of which being creating a device with multiple degrees of freedom of motion. Current prosthetic devices have very limited degrees of freedom of motion. Flexion at the elbow, maybe wrist rotation in the transverse plane, and maybe hand opening and closing. And as we all know, the normal human upper extremity has many more degrees of freedom of motion than that. And to conclude, as a final control mechanism, was I think you can see that the technology is there. It's how do we control it, and that's where a lot of the science is being focused on right now. Is there are projects where we can essentially, or that are working toward essentially connecting the prosthesis directly to the central nervous system, to the brain. Here at UCSF, for example, we have the CNEP, the Center for Neural Engineering and Prosthesis, which is a UC Berkeley, UCSF joint project to create prosthetic extremities at this point for spinal cord injury patients. But I think the long-term intent is to also incorporate that into the prosthetic community. Other groups are working hard at work at implanting small electrodes in the periphery to allow for very fine point dexterity of a prosthetic hand because they're putting isolated electrodes in the muscle groups that would function the hand at a very fine level. And with that, I think we have concluded our talk. So thank you very much for listening.